So let's, all right. Good morning, QED coders. This is Michael. Today, let's go ahead and talk about the book a little bit, but I want to approach this from a slightly different angle. So, for those who are not yet familiar with the channel and the Discord, we are talking about the art of immutable architecture, theory and practice of data management in distributed systems, and this is something that's that I've been spending quite a bit of time on. It looks like we have a guest. Hey, I believe
Hello.
that is Caleb. Or I'm sorry, I just blanked on your name again. Not Caleb, but
Yeah,
um, yeah. I'm afraid I blanked on your actual name.
Kaden. Kaden.
Kaden. Yes, Kaden. Very good. Good to see you. Yeah,
Yeah,
I.
I was busy correcting the exam of
Mhm.
our course, so I just forgot uh, the book club last week. Yeah.
Not a problem at all. Yeah, so last week, Jan and I were talking a bit about the Janaga open source project, and this week Jan is not able to join us, so
Oh,
yeah, we can spend our time talking about anything that you're working on, and I also have a presentation that's kind of the ideas of the book from a different perspective.
okay. Cool.
So, um, so have you? Um, yeah, how far have you gotten in the book so far?
Um, I don't have much time reading, so I just read chapter one for now.
Okay,
Yeah, just get started.
okay. So this might actually be a really good overview for you.
Okay.
Okay, so I will return to. There we go. Let's. So yeah, I should be. Yeah, I should be sharing my screen with the
Yeah,
presentation.
I
All
see
right,
your
awesome.
screen.
Yeah. So basically, what I'd like to start with is this idea of model view controller. So we've seen um, some libraries in the past that are based on this idea that you've got some model that changes over time. Uh, you've got controllers that will influence that model to cause changes, but also pull data from that model in order to provide it to a view, and then the view renders the model, renders that information for the end user, and also accepts the end user's inputs, and then the controller turns those back into changes to the model. So this is a paradigm that's based on the mutation of that model over time. And one of the big problems in model view controller is notifying other controllers of changes to the model and keeping everything up to date. So so that's something that yeah, that we've been kind of struggling with, and things get kind of complicated as these MVC applications grow. And so, have you used React?
I know that,
Ah,
uh, but I haven't. I only go to the example project.
okay.
I haven't really used it for the real project.
Well, good. So you've probably been introduced to this idea of model view update. So that's one of the core
Yeah.
ideas inside of React. And for a model view update, you have your model as you did before, and then a render function turns that model straight into a view. You don't have a controller that's doing that. It's just a pure function. So that render function can't change the model at all. It just projects a view. And then the user is presented with that view. They make some kind of decision, and that decision generates an action. So they click a button or drag drop or whatever they're going to do to produce that action, and then that action is applied using an update function. So that update function takes two inputs, the action and the model. And then what it does is it produces a new copy of the model. It creates basically the next generation of the model. So it doesn't change the model that's already there. It produces a new one. And so if you take this model view and action and take that cycle and you extrude that through the time dimension, then what we're really showing is there are multiple versions of the model over time. Each one is projected into a different version of the view, and then as the user is interacting with those, you've got different actions that they perform. So this is the, when you add the time dimension, this is how it becomes an immutable way of working with applications. And that makes it a lot easier to reason about. Solves a whole bunch of threading problems and notifying others of changes. It's just simply projecting a new version of the view from that new version of the model. So it really simplifies things. So
It's cool to see it,
mm-hmm.
view it as a 3D model. It's very cool to see that.
Yeah. I had a lot of fun putting that together because, you usually think about these things in terms of just the relationships of these objects as a snapshot in time, but yeah, time is a dimension that you really have to think about.
Yeah.
So the picture of what we want is we've got these different versions of the model. Here I've dropped the view from the picture, and time is just going across the page. So you've got different versions of the model, and then you've got actions. So action plus previous version of the model produces the next version. And the way that we will typically write that in a React application, actually, it's kind of funny, I wrote this example in pseudo C#, but yeah, could have written in TypeScript, is that we've got a copy of the current model, and then we've got our apply function that updates that model from the action and then overwrites that previous version with the new version. So that's a way of thinking about the operation that we're performing. When we think about implementing this idea in something like Redux, basically Redux has this behind the scenes, and we are presented with this update function, or we get to write this update function. So Redux says, hey, give me a function that takes a model and an action and produces a new model, and I'll take care of the state for you. So this option, or this operation of applying an action repeatedly to get new versions of a model, that's an example of a left fold. So this is just a term for applying a function over a collection of inputs in a sequence, starting at some starting state, which we'll call x0. So you take x0, you call your function with x0 and e1, and then that produces x1. Call it again with x1 and e2, and that produces x2. If you were to take, for example, x1 being the integer 0, and all of the e's being a list of integers, and then the function being the plus function, then the left fold would just be add up all the integers. So it's a useful operation, and one that we find that we do a lot of computing on. Like in fact, anything like MapReduce is a left fold. Um, the reduce part of MapReduce is just left fold over a sequence of things that were the output of a map in order to reduce it down to a single value. So the left fold operation definitely comes up when we're talking about a sequence of operations and finding the end state after that sequence of operations. And it also comes up in distributed systems. So in a distributed system, you'll have each different node, each different machine within the system, starting at some initial state and receiving a sequence of events, and then running the left fold in order to compute the final version. In fact, this might look familiar to you. Have you worked with event sourcing?
You mean event sourcing?
Yes.
No.
Yeah. So event sourcing is a form of immutable architecture. So you'll see that I talk about it a little bit in I believe in chapter 3. Might be at the end of chapter 2 that I start talking about event sourcing and how that plays into the book. But yeah, if you were to take all of the different events that have occurred on all of these different nodes and put them into some event store that puts them in order, then that produces a reliable order that all the different nodes can depend upon in order to run those events and compute the current state.
Oh, it sounds like Apache Kafka.
Hmm?
Is that right?
Yeah, yeah. Kafka is a good example of an event store. Yes.
Then I know some of this.
Okay, excellent. Yeah, yeah, yeah. There are other. Actually, there is a product called Event Store that was created by Greg Young, one of the first people to really talk about event sourcing and to design systems this way.
Okay, cool.
Yeah. But there's another system that you're probably familiar with that works this way. What if instead of calling these events, we call these commits?
Oh, yeah.
Yeah, and now you've got your main branch is a sequence of commits, and then each of your working branches is another sequence of commits that you tack onto those, and so when people are working in Git, they can now work autonomously. They can do their own work and create their own commits on their own machines within their own branches. So in this case, we've got a developer on working branch 2 working on his local machine, and another developer on working branch 3 working on her local machine, and so they've each created commits, and so what they then want to do is push their their branches to the remote, and they ultimately want to get them into the main branch. So developer 3 gets her commit in before developer 2, and so we end up with the main branch in this particular order. So the challenge then becomes how do we get everybody up to date with what the main branch looks like, and so everybody does a pull and gets all of the commits back down to their machines. And for developer number 1 over here, they haven't contributed any commits, so they just get them in the correct order. Developer number 3, since she got her commit in first, she pulls developer 2's commit, and it plays in the proper order. But developer number 2 has already seen their own commit, and now he has to somehow contend with this other commit. And so he's going to perform an operation called a rebase in order to get that commit into his working branch in the correct order. So sometimes you can rebase and everything's fine, but sometimes you end up with a merge conflict. And that's kind of
that's a pain.
Yeah. And that's a reflection of the fact that sometimes order matters and sometimes it doesn't. So if you've got two different machines, two different left folds, and you perform the left fold with the events in one order, you might end up with one state, but you perform that same left fold with the events in a different order, you'll end up with different states. And the question is, are these resulting states equal to one another? So if we go back to the example I gave about the plus operator, where x0 is the number 0, would those states be equal?
Sorry, I forgot that.
Yeah. So if the function that we were applying was to add a number to the previous state, and then I give you a list of numbers, and then I just change the order and I give those same numbers to you, and you just add them together in a different order.
So that doesn't matter.
Right. Yeah. Exactly. Yeah. So do you know the name of the property of addition that means that it doesn't matter?
Yeah.
Yeah, that's kind of digging back there in our elementary education, but that's the commutative property. So if if your function is commutative, like the add function is commutative, then you can prove those resulting states are equal. So this kind of gets into the CRDT stuff that we were talking about before, is that one of the conditions of the CRDT approaching a strong eventual consistency is that the operations are commutative. That when you apply an event, you apply an update, it doesn't matter the order in which you've applied those updates, you will still reach the same result. So that's a necessary condition for strong eventual consistency, and it's a necessary condition if you are going to build a distributed system in which things can arrive out of order. For event sourcing and other systems that don't have or don't enforce the commutative property, they've got a different way of achieving that, and that is to force everything to be in the correct order. So in Kafka, if two events are posted to the same topic, then they're going to land in the Kafka log in a particular order. But if you post them to different topics, then the order in between them is not going to be guaranteed, and so you could be reading from one topic and reading from a different topic and get those in the opposite order that they were written. So
yeah.
So it's really up to you as an application developer to understand, are your functions commutative or are they not? Because sometimes order matters and sometimes it doesn't.
Mm-hmm.
So that's what the sort of analysis that I talk about in the book strives to do, is to identify when does the order matter and when does it not matter. So when it matters, what I want to do is to draw an arrow to the previous event. So I'm saying this event has to happen after that predecessor. And I can have multiple arrows coming from different predecessors. So I can say this event has to happen after that one and after this other one way back in history. But the arrows can't go the other direction. I can't say this event has to happen before, or I can't say this event has to happen after something that hasn't happened yet. So I can only point back in time. But by being explicit about this order, that allows me to then rearrange this linear sequence of events and create a distributed acyclic, or a directed acyclic graph. So yeah, I know that like in some of the research that you were sharing with us, you were talking about graphs and how things are connected to one another. So so you showed an example of a ring buffer that
Yeah.
deliberately had a cycle in it. That's kind of the feature of that graph. That was an important feature of that graph. So have you done any study on acyclic graphs?
I've taken a course about the basic graph theory.
Mm-hmm.
Just some basics, not so advanced.
Yeah, yeah. Directed acyclic graphs (DAGs) have some really interesting properties. So one of those properties is that there's a topological order, at least one, that you can find within a directed acyclic graph. And the topological order is basically rearranging the graph so that it is in a linear sequence. So so you can take any graph that is a DAG, so it has no cycles, and you can say, let's just pick one node. Let's start here. Say, can I write this to the sequence first? Well, let me check. Does it have any predecessors? It does have a predecessor, so I can't write that first. Let me try to see if I can start at this one. Nope, it's got predecessors. Let me see if I can start at this one. You find your way to a root node. There could be more than one. In this case, I only have one root node. And so I say, okay, it has no predecessors. I can go ahead and write that to the sequence. And now that I've written it, I can go down either direction. Can I write this one? Can I write this one? And in this case, neither one of these has another predecessor. All of their predecessors have already been written to the sequence. So I could write a sequence starting 1, 2, 3 or 1, 2, 3. It doesn't matter. Both of those are correct topological orders. And so I can take this directed acyclic graph, I can linearize it, and then if I wanted to, I could perform a left fold over those operations. And as long as those arrows represented when order matters, then I'm guaranteed to get the same answer at the back end. So this is a really good way of generalizing the problem and saying that sometimes my operation is commutative and sometimes it's not. When it's not, there's an arrow, and when it is, there's no arrow.
Okay.
And so in a lot of cases, most of the time, there's no arrow. Most of the time, operations are commutative. And so what I like to do is to take a problem space and then analyze that in terms of the decisions that are made within that domain. And then the predecessors are the prior decisions that you had to know about in order to make your decision. So this is just taking the idea of the kind of this abstract idea of these different circles within the graph, and turning them into something real, an actual decision that somebody makes. So and I call that a historical model of your domain. So this is an example of a historical model of a speaking domain. So we've got a conference organizer who decides to host a conference. So that decision is captured as the conference right at the top. And then they will publish a call for speakers, and they'll say, okay, I need somebody to come and speak at this conference. Here's all the information about the conference, and now please submit your proposals. And then a speaker, on the other hand, is going to sign up for some service. Like there's one that I use called PaperCall. That's pretty popular. Sessionize is another one. And so they will create that account as a speaker, and so that's the decision to create that account. And then while they're on that site, they will create an abstract and kind of put that into their profile. So having the abstract and the call for speakers, they can now decide to submit that abstract for that call for speakers as a proposal. So the proposal can't take place until you have an abstract and a call for speakers. So both of those are predecessors. But look at the abstract and the call for speakers. There's no arrow between them. So what does that mean? About the order between those two?
They are communicative.
Yeah, exactly. Yeah, those commute. You could have the call for speakers before the speaker has written the abstract, or they could write the abstract and just have it waiting for a call for speakers. I've done both of those myself. So somebody has a call for speakers out there, and I say, oh, that's a really interesting conference. I see what their theme is, and I've got this idea that I think will fit in with that theme, and so I write an abstract. Other times, I've already got the abstracts up there because I've presented them, or because I'm really interested in presenting them, and I just have them up on the site. And then I see a call for speakers, and I say, okay, that abstract would be perfect for it. So those two can happen in either order, but the proposal has to wait for both of them to have occurred. And then once proposed, the organizer takes all those proposals for that call for speakers, and then they can accept some, reject others. So they make another decision to accept or reject. And then only the ones that are accepted then get scheduled, and so they're given a time and a room within that conference. Then a third actor enters the scene, and you've got an attendee who will then be able to see the schedule for all of the sessions at the conference, and then choose to attend certain ones. But then only the ones that they've attended will they be able to rate. So they can tell the speaker how well they did, and they can tell the conference organizer if they want to invite that speaker back again next year. So this is a historical model of all of the decisions that are made within this domain, and the arrows represent when order matters and when it doesn't. So there's some interesting things that you can learn, that you can kind of glean from just this model. Just by doing this analysis, you can determine what's going to what's going to be possible within your distributed system, what's going to be a challenge, and how your messages are going to flow. So you see the dotted lines, the boxes, the regions around different decisions. So when an arrow crosses one of those boundaries, that seems like that's a really interesting occurrence. And in fact, what that indicates is that one person is interested in a decision made by somebody else. So in a distributed system, you will often have the different nodes within the system have some affinity to different kinds of actors. So there might be a microservice that's intended for the speakers to use, and a different microservice that's intended for organizers to use. And so when the arrow crosses that boundary between speaker and organizer, can you guess what's going to happen in the distributed system, in that microservice architecture?
there may need some resolver.
Mm-hmm. Yep. Yep, exactly. You're going to be sending messages from one microservice to the other, and you're going to need to have a resolver to take that information and bring it into the that other microservice's database. Yeah. So as
Yeah.
a speaker, you're going to need to see the calls for speakers. That was a decision made by an organizer, and so that was put into a different microservice, and then you subscribed to that message. You got that call for speakers, and then you've brought that into your database. Yeah, sometimes, like that one will probably be a search of a remote database. You probably don't want to bring all calls for speakers into your system because you're really only interested in a handful of them. But then going back the other way, you definitely do want to bring that in. So if somebody submits a proposal, as an organizer, you want that in your database. And then as you do the accept and reject, now you are making a decision within your database, but you know that the speaker is interested in that. That's the reason they sent that proposal. And so you have to send the message back. And so every time the line crosses, you've got some communication between these microservices. And if it crosses twice, then you've got this conversation that's happening. So some of these boxes represent end user devices, like the attendee has a phone. And at a conference, Wi-Fi is typically not all that great, and so their phone needs to have a subset of the data. So in order for the attendee to be able to attend and rate those sessions, they will need a subset of this graph on their device. So another thing you can learn from the graph is, what is that subset? What's important to the attendee? And you can do that by performing an operation called a transitive closure over the predecessor relationship. So starting from the schedule decision that they so the attendee wants to attend a particular session. So starting from that schedule decision, they'll need to have all of the information about all of its predecessors. So they'll need to know the time, the room, and then the accepted proposal. So they'll need to see the abstract of that proposal. They'll need to see the speaker. They'll follow those arrows up the history, and that will give them a subset of the graph that includes the call for speakers. It includes the conference. It doesn't include the reject. They're not seeing any of the rejected proposals. So that's not part of their subset. But the other facts, the other decisions that were made along the way, that is part of their subset. That's what they're interested in. And so you can perform this transitive closure in order to find a subset. And the really cool thing about a transitive closure on a directed acyclic graph is that produces another directed acyclic graph. It follows all the same rules. So that is now the subset that you store on the local device. And that's how a historical model can help with different architectures. We have microservices, searching across remote databases, and loading subsets into mobile devices. So basically you take your topology and you take your historical model, you bring them together, and that informs your architectural decisions. That gives you data models and messages and all the stuff.
So how about uh, the speakers or abstracts changed over the time? So the
Excellent question.
attendee may get some some wrong information.
Mm-hmm. Yeah, that is an excellent question. So the abstract that we're talking about there, if it contained the actual text of the abstract, then that would mean that within this model, that text cannot change. Each one of these historical facts is immutable. It's not allowed to change. Now, of course, you show this to a stakeholder, and they'll say, "Well, I need to be able to edit my abstracts. That's
Yeah.
a necessary part of the system." And so, what you then have to do is create another fact that is the text of the abstract. And so maybe where we see the abstract fact, that is a talk, and then the abstract is a successor to that talk. And so we've got a different fact. So whenever somebody wants to update their abstract, they're creating that new fact. And now, as you rightly pointed out, that new fact about the abstract is not part of the transitive closure anymore, because the transitive closure just follows the arrows up. It doesn't follow the successors back down. And so that has revealed to you that you need to have another message. You need to publish messages when somebody changes their abstract, which
Yeah.
you might have figured out by testing your way to it and seeing that things get out of sync if you don't have those messages. But you could also mechanically run that operation, find the things that fall out of the transitive closure, and then that mechanism tells you that that you need that message.
Okay.
Yeah, so there are some patterns that kind of emerge as we're turning a domain into a historical model, and we'll see this idea of changing the value of an abstract, for example, come up as part of these patterns. One of those patterns is that you've got stages in a workflow. So in a lot of systems, we keep track of the current state of an object as a single property on that object. So in a purchasing system, we might have the state of an order. Has the order been invoiced? Has it been paid? Has it been canceled? Has it been refunded? These would be states, but a more representative way of looking at that would be to take a look at the different decisions that led to those state changes. So somebody placed an order, and then the accounts payable system saw that order and said, "Okay, here's an order without an invoice. I'll go ahead and create the invoice." And then that gets posted on the customer's portal, and then they can go into that portal and submit a payment. So when they do, that creates the payment decision. So which invoice have they paid? That particular one. So that payment points back to the predecessor invoice. And now we can see that that order, having been invoiced, is now paid. And we've got that entire history. And so all of the information that we're capturing along the way are also changes to the state of the order. It's all done as one atomic operation. And within the stages of a workflow, you can now take all of the different edge cases into account, so the things that might happen concurrently. So let's suppose somebody cancels the order before we've invoiced it. Okay, well, now we know that we don't need to invoice it, but then if we do see the invoice come through, oh, that system just didn't learn about the cancellation in time. Now we've got the invoice. What do? We just don't show that invoice to the customer. They don't need to see in their portal invoices that for orders that have been canceled. But what if they didn't receive that cancellation in time? Maybe they've got a different department that's paying those invoices, and they've already submitted a payment. Well, then by the time we learn about that, we see that the order is canceled, but it also has an invoice and a payment, and now we need to issue the refund. So we can find those shapes within the workflow, and we can respond to them appropriately. So that's one of the patterns that comes up quite frequently, and we saw a lot of that in the speaking. Now, another pattern that comes up pretty frequently, and this is kind of related to the abstract idea, is we've got mutable properties. since we can't actually change a historical fact, they are immutable, then we have to somehow model immutability. And this is what we do to model immutability. So we've got the entity, maybe the entity is the talk, the session. And then the entity property, you might have an entity property that represents the title, another entity property that represents the abstract. Entity property 1 is a fact, a decision to set one of those to a particular value. So let's just talk about abstract. Entity property 1 is the first abstract that you write for that session, for that talk. Then entity property 2 is the decision you make when you go in and you edit that abstract. If you were to edit the title, that would be a different part of the graph entirely. But when you're going back and editing the abstract, you are replacing one abstract with another. Now, you can't go back and edit that fact, but instead what you do is you create a new fact and you say that the prior version of the abstract is entity property 1. And so doing this over time, you'll end up with this chain of versions of the abstract. And if you take a look at this directed acyclic graph and compute the leaves of the graph, you'll find yourself with just one leaf, entity property 3.
Ooh.
Mm-hmm. So I think you might be able to see what happens here. This is what sequential edits look like. But if you've got concurrent edits, where two different people are editing the property, then you'll end up with a different shape. Entity property 2 is made with the prior knowledge of entity property 1, but entity property 3 was also made with the prior knowledge of entity property 1. It didn't know about entity property 2. And so concurrently, you end up with a different shape. You end up with a graph that has two leaves. So if you've got more than one leaf, there has been a concurrent edit, and we can resolve that. And so the resolution looks like somebody coming in, making a decision. Is the actual value for entity property 2 correct? Or the actual value for entity property 3 correct? Or is there perhaps a different value? Whatever that value is, they record that inside of entity property 4, and that has two prior predecessors. So that replaces both 2 and 3. And so in Git, this would be a merge commit. This is a commit that has two predecessors. And so we'll use that to represent conflict resolution. And that's a pattern that emerges quite a bit. So the last pattern to talk about here is the deletion pattern. So facts are not mutable, so you can't change them. You also can't delete them. You can't destroy them. And so if you want to represent the deletion of a fact, then you've got a tombstone. You've got another fact that points back to it that says, hey, that thing has been deleted. And so when you look at this graph, what you're looking for are all of the order lines such that there does not exist an order line deletion. And that's a query that you could write in SQL. I do this all the time in relational databases. A lot of people will do a soft delete by having a flag on the record itself that they set to 1, but that's an update of the record, and I don't allow updates. So instead, make that a new record in a new table, because this is a new type, with the foreign key back to the one that you're deleting. And then that turns into a where not exists query. But sometimes people make mistakes, and so you might want to extend the deletion pattern to also allow for restoration. So now you're looking for order lines where not exists an order line deletion, where not exists an order line restoration. So this is something that that I implement quite a bit in relational databases. So I use those foreign keys to represent those predecessor relationships, and then I'll do those where not exists type queries in order to compute the current state. And that way, my relational databases allow only inserts, no updates, no deletes. So insert and select; those are the only two operations that I allow. And I've got this full history of these immutable facts that that if the order matters, I've got this foreign key relationship. If the order doesn't matter, no relationship. So everything is can be played in either order. It also affects message design, doing the transitive closure as we talked about before. So starting from a particular fact, perform the transitive closure. That gives us all the facts that led into it. Everything outside of that cone, looking back into the past, are not part of the transitive closure. So all of this kind of culminates in the kind of architecture that I'm trying to prescribe here. So if you've got a microservice that's interested in this subset of the graph, maybe this is the sales service, so somebody's submitting an order, then it can send a subset of that graph over to the payment service that's interested in creating invoices and receiving payments and issuing refunds. And then you've got that sending messages over to the shipping service, which is now interested in the logistics of shipping those orders to the customer. And maybe you've got returns that are happening as successors to some of those orders. And so if you combine all of these together, we could build this system using the technologies that we're used to right now: relational databases, Kafka, other messaging systems, or we could build a new kind of runtime, a new kind of substrate that all of these systems can work on, and so if we can compute the interest, what subset each of these subsystems is interested in, then we'll have this substrate that has all of the information encoded within it, but none of the applications have the full picture. Instead, they just have the subset that they're interested in. And that will allow us to build a system that scales extremely well, and we can add new capabilities to that system by then participating in this substrate. And as long as everything can be automated and we don't have to manually come up with what are the messages that we need to send, then we can encode all of those rules into an immutable runtime. And that's the reason that it's really important to me that things like transitive closure makes it possible for message design to just automatically emerge. I don't want a human doing that in the long term. I want the machine to do that as part of the immutable runtime. So that's really the picture that I'm painting in the book.
Well, cool. Thanks for the overview. That's pretty clear.
Awesome. My pleasure. Yeah.
So I have a question about how about the assumption that some communication might be malicious.
Yeah.
I mean, yeah, the situation you just mentioned is like every action is in trust, and all of them are legal. So how about like one of them are malicious or intend to do something is not really good?
Yep. Yeah. What I didn't go over there was a set of rules around security. So so if you've got a malicious actor that is trying to convince you of a particular fact, they've made a decision, and they're trying to convince you that somebody else made that decision. I use cryptographic signatures in order to prove to you that a certain actor made this decision, and then I've got a set of rules for how you can check that signature against the shape of the graph, and create authorization rules. So only these people are allowed to make these decisions. And then you can roll that into the graph by having some of those facts in the graph represent actors. So the speaker, for example, actually captures the public key of the speaker. That way, you can then verify the the proposal from that speaker. You can verify that signature, and know, okay, it was actually this speaker who submitted that proposal.
Oh, that sounds.
Yeah, that's part of what what the meat of the book gets into is okay, that's the dream. That's what we're trying to accomplish. What are some of the what's some of the meat that what are some of the things that need to be done in order to achieve that dream? And security is a big part of that. So who's authorized to do something, who is allowed to see certain decisions. So that's a different set of rules. So we'll often in our systems have our read security and our write security and kind of mix them together. We've got role-based authentication. You're allowed to read these things. You're allowed to write them. You're allowed to administer them. But those are actually different concerns. And so I take those ideas and I separate them and I say, okay, the write security is enforced with these public keys and the cryptographic signatures, but read security that has to be enforced in a different way. So you've got encryption of the contents of a fact. So you have to have the shared key in order to decrypt it, and so there's a way to share a key within the graph in such a way that only people who have the privilege of reading that fact will be able to read that shared key. But that still leaks a little bit of information, because even if you can't read the contents of the fact, you can read that there is a fact and it's related to these others, and you can kind of get the metadata. And so I also encode those as distribution rules, so that the different nodes through which these facts flow know not to distribute these facts to people who aren't allowed to read them. So that one, I lock it up in two different ways: cryptographically and topologically.
Cool. So yeah, I have this question because that I've seen some algorithms that trying to solve the Byzantine fault tolerance. So
Yeah.
they make the algorithm more complicated and even more uh, inefficient. Even more inefficient.
Mm-hmm.
So I mean, maybe separate that is the better way, better
Yeah.
than making the original algorithm more complicated.
Yeah. Yeah, and Byzantine fault tolerance also protects against things like denial of service attacks. So there are some things that this model doesn't protect against. So it's not fully Byzantine fault tolerant.
Yeah.
So yeah, it's still relying upon you running the infrastructure in the right way. And so rate limiting and looking for those bad actors on your system, and those problems don't go away with this model. But some problems do, and some problems you just simply have a better vocabulary for talking about them, and you can enlist some help from the mathematics and from the immutable runtime.
Yeah, and some are just social problems. I think
Yeah,
they
yeah,
can be solved by social.
yeah,
Yeah.
indeed. Well, cool. So yeah, thank you so much for joining and discussing that with me today. And yeah, I'm glad that I had a chance to get this out there for folks that haven't yet read the book. It's the book is presented in a different in a different way than this this information. But after having published the book, I was like, what, this is something that I think speaks to to developers who are familiar with React, who are familiar with Git. It'll kind of get them into the flow of thinking this way. So I hope that
Yeah.
you found it useful and you'll be able to apply it in your research.
Yeah, pretty helpful. Thanks.
Awesome. Well, then I will be back next week. Hopefully you'll be able to join us then. Jan will be back as well. So
Okay.
yeah, we'll see you then.
Bye bye.